Hello everyone and welcome to Newton's third law of motion. Even after many years, if someone asks you what are Newton's laws of motion, I guarantee even if you forget the first two, you're going to remember the third law because it's simple and straightforward. It merely says that to every action there is always an equal and opposite reaction. Equal means they are equal in magnitude and opposite means they are opposite in direction. Now, we've all heard about Newton's third law, so let's quickly review it by taking an example. You can see in this case, we have a swimmer that's trying to push off against this wall and gain some momentum to go swimming to the other side. Now, very quickly, we can identify what is the action and reaction in this case. It's very simple to see that the force acting because of the swimmer on the wall will be counted as the action, and the wall in retaliation will exert a force on the swimmer which is known as reaction. In fact, we've heard of this before. It's nothing but the normal reaction exerted by any surface, right? So this is the action-reaction pair. Let's quickly understand what else Newton's third law tries to tell us. Well, firstly, it's saying that whenever one body exerts a force on the other body, then the other body will also exert an equal and opposite force on the first body, which means that forces must always exist in pairs. Of course, if I'm telling you that every time a force is acting, there is another force acting in retaliation, it means forces must come together in pairs always, which means a single isolated force is not possible in nature. Finally, Newton's third law is also telling me that action and reaction act on different bodies. And this is very important. Take a look at what is happening in this picture. The action is because of the body on the wall and the reaction is because of the wall on the body. So they are acting on different bodies. And why is this important? Because even though they are equal and opposite, they are not cancelling out. And they don't cancel out because they are acting on different bodies. So this is very important to remember that action and reaction act on different bodies. So quickly let's identify the action and reaction pair for some other examples. We all know about rocket propulsion. In the propulsion of a rocket, we know that the pressure of the gases inside the chamber builds up and finally the rocket thrusts these gases out. That is, the rocket exerts a force on these gases and they come gushing out. And this is what we will identify as the action of the rocket on the gases. In retaliation, the gases push the rocket up and that's your reaction. So this is the action-reaction pair for a rocket. It's the principle of rocket motion. The next case that we will look at is the recoil of a gun. When a gun shoots a bullet out, the gun is exerting a force on the bullet which I'll identify as the action. But in retaliation, because of the force exerted by the bullet on the gun also goes back a little, which we call as the recoil of the gun, and that's your reaction. Finally, let's look at one more example, that is rowing a boat. When you are rowing a boat, you are pushing the water backwards and that counts as the action. But because of this pushing, you tend to move in the forward direction because the water is giving you a reaction which helps you move in the forward direction, and this is your action-reaction pair for rowing a boat. So we saw some identification of action-reaction pairs, and this is Newton's third law of motion. Another thing I want to talk about is what is meant by a frame of reference. Well, frame of reference is nothing but like your Cartesian coordinate system. But why do I need it? I need it because if I do some physics calculations in my room and you do them in your room, then our physics should match. It can't be that I have one law and you have a different law. And this can only happen when we decide to follow the same rules. Like for example, let's all decide that the forces acting to the right are positive and the forces acting upwards are positive, or some such rules that basically give us both the same foundation which will lead to the same physics no matter where you are. And one of the steps to doing that is to decide together what frame of reference you must use. So simply speaking, a frame of reference is nothing but a system of coordinates with reference to which the position or motion of an object can be defined or described. Frame of references are of two types. First one is an inertial frame of reference and the second one is a non-inertial frame of reference. Simply speaking, an inertial frame of reference is that which is fixed or moving with uniform velocity relative to a fixed frame, which means inertial frames are those frames which have no acceleration. You are either at rest or you are moving with uniform velocity. These are known as inertial frames of reference. And they are very important. You can see from the word itself, inertial has something to do with inertia, which has something to do with Newton. And therefore, they are important because Newton's laws hold very well in these frames of reference. On the contrary, in the non-inertial frame of reference, now you should guess that Newton's laws must not hold in these non-inertial frames of reference. And what are non-inertial frames of reference? Well, they'll be those frames which have acceleration, which means they are moving with an acceleration relative to a fixed frame of reference, and these are known as non-inertial frame of reference. Incidentally, the next question that should pop in your head is that is Earth an inertial frame of reference? And this is important because after all our experiments and calculations are done here on Earth. So is Earth an inertial frame of reference? Well, strictly speaking, Earth is not an inertial frame of reference. This is because the Earth is rotating not only about its own axis, but it's also orbiting around the Sun. And because of this, there is centripetal acceleration present in both these motions. And therefore, it means Earth is an accelerated frame of reference, which means it's a non-inertial frame of reference. But then, how can I consider it to be a non-inertial frame of reference and then do all the calculations on Earth? Which means Newton's laws must not be applicable anywhere. Well, for practical purposes, because the velocity of the Earth is so small in most calculations, we do consider it to be an inertial frame of reference, but technically speaking, it is not. Finally, let's do a small exercise wherein we classify the following cases as inertial and non-inertial frames of reference. Let's take the first one. I ask you, what is this frame of reference when you have a car at rest? Well, it's straightforward. The car is at rest. There is no velocity, which means there is no acceleration even. And if there's no acceleration, means the body is at rest and it's an inertial frame of reference. So let's classify it as an inertial frame of reference. The next case is a lift that is going up and speeding up. So it's not only going up, but it's also speeding up, which means velocity is increasing, which means this is accelerated motion, and I'm going to put it under the category of non-inertial frame of reference. The next one is an observer on the platform observing an accelerated train. Well, this is tricky. I'm not asking you about the train. I'm asking you about the observer. The observer is simply on the platform, which means he's stationary. And therefore, because he's not moving, it's actually just a body at rest. And therefore, I categorize this as inertial frame of reference. Next one is a roller coaster. In a roller coaster, your speed goes up, its speed goes down. That means your acceleration is present, and therefore this is accelerated motion. I classify this as non-inertial frame of reference. The next one that we have is to ask what happens if a bus is moving with uniform velocity. Well, it is moving with uniform velocity, which means no acceleration, and therefore I have an inertial frame of reference. And finally, I have the last one to ask you a frame fixed to the earth. Well, we just discussed that an earth frame is actually technically not an inertial frame of reference because it's an accelerated motion, and therefore I classify this as a non-inertial frame of reference. So we discussed Newton's third law and frames of reference. If you like the video, please subscribe.